So, let's go and just think back to where we left off last time. So, we had talked about different types of exponents, and we have to use different techniques for different exponents, right? We have natural number exponents, that just means multiply something by itself some number of times. But for different exponents, we have to use different ways of computing them. And we talked about irrational exponents, that one way we can compute irrational exponents is using a sequence of rational exponents that get closer and closer to it, right? We mentioned that that's not really the best way of doing things, and that there's a better way using Taylor series. And so we left off talking about a couple of important Taylor series, right? We talked about e to the x, for example. And it had a couple of closely related Taylor series, right? That we mentioned that sine of x is -2k minus 1 to the k over 2k plus 1 factorial. We mentioned that this is closely related to e to the x. We also mentioned that cosine x is closely related to e to the x. We're going to use all three of these quite a bit in today's discussion. And so these are actually what we're going to use to define complex exponents. Okay. And so before we start talking about complex exponents, let's first talk about real exponents that happen to be irrational, okay? Because last time we calculated 5 to the square root of 2 by taking a limit of rationals that approach the square root of 2. But I mentioned there's a different way of doing this. And so the way we're going to do this is using Taylor series for the exponential function and Taylor series for logs, right? And the motivating idea here is that 5 to the square root of 2, we can rewrite this in terms of base e, right? We know that 5 is really the same thing as e to the natural log. I'm just going to write log here. Pretty much it's the only base that mathematicians ever use is base e. And so mathematicians, they'll just write log meaning base e, okay? So e to the log of 5 is 5, right? So let's rewrite this using that expression for 5. And then using the properties of exponents, we know that this is equal to the product of these things, e to the square root of 2 log of 5, right? And so it may look like we're taking this, a step in the wrong direction. It seems like we took something that was relatively straightforward last time and we're making it even more complicated by expressing it in this way, right? But what we're going to do is we're going to take a look at the log in terms of a series, okay? And so on the screen, you'll notice that we've got a bunch of different expressions for log base e here. And all of them are slightly different, right? So the first example let's consider is this example here, natural log of 1 plus x. Then what they've done is they took this natural log of 1 plus x and they expanded it out into a Taylor series centered at 0, okay? Taylor series centered at a equals 0. And the reason they did this little shift here is because it's a lot easier to have a Taylor series centered at 0 than it is to have a Taylor series centered somewhere else, right? So in this first line here, log of x, they said, okay, let's take the log centered at 1. And you'll notice that when you do that, the expression is slightly more complicated, right? So the idea behind this natural log of 1 plus x is that you can center it at 0 and you get these really nice powers of x. They're really clean, right? So that's the other alternative, is you can of course just take the Taylor series expanded around a equal to 1 of the log. But there's a couple of problems with these expressions, these Taylor series, which is that each of them has a very limited domain of convergence, right? In this expansion here, the domain of convergence for this thing is only from -1 to 1. And domain of convergence for this one is from 0 to 2. And so let's take a look at what that looks like. There's a nice Wikipedia article that shows how these things behave outside of those domains. Sorry, I should have this up early. I'll just do this. Okay. So where are we with begin? Okay. Taylor series. Log. Okay, that's what I wanted. So it's only well behaved on that very limited region. So here's where they took that 1 plus x. They just took the logarithm, like I said, they shifted it to the left 1 unit. The idea there is that you can now center it at 0, so you get that nice expansion with nice powers of x. And so what happens is, on that interval from -1 to 1, you'll notice that the Taylor polynomials are closely approximating the function. This blue one is up to the 16th order Taylor polynomial. But then right here at 1, you'll notice this funny behavior where the Taylor polynomials start rapidly deviating away from what we think the log should look like, right? The log should be this nice curve going up like this. And so we notice that right around this point, they start diverging wildly. And so the Taylor series that you get for logarithm, it's only sensible on this very small interval. And so there's a whole bunch of stuff you have to do to get a nice series expansion for log that works everywhere, okay? But it starts with the Taylor series, and then you can start modifying it using a bunch of different transformations. And so when you modify the series in the appropriate way, you can get a series that works for the log on the whole real line, okay? And so here we go, log of x can be given by this series here, x minus 1 over x plus 1, and you take powers of that thing. And so that works for all positive x's. So this is the guy that we want, right? Because what we've done here is we've defined the logarithm in terms of an infinite sum, where each term uses addition, subtraction, multiplication, and division, right? So this is the one we want, because it gives us log x using only addition, subtraction, multiplication, division, and then of course limits to actually compute the sum, right? So what we've got then is the next in-between step that we need to compute something like 5 to the square root of 2. Because we have this 5 to the square root of 2, it's really the same as e to the square root of 2 log of 5, right? And so, what is that equal to? We know the power series expansion for e to the x is this guy here. You know, take the input to sequential powers of k over k factorial. And so we've reduced this down to this term here, can be computed using addition, subtraction, multiplication, division, and limits. Compute that guy, plug it in here, and what do you get? You get a term, you get terms that are nothing but addition, subtraction, multiplication, division, and limits, right? And so we've reduced irrational exponents down to those 4 basic operations that we can make perfect sense of, right? And so in general, that's the way you compute irrational powers, is if you have a to the b, then the general formula says rewrite a with base e, and then raise that to the b power, which is then e to the b log of a. And so this here can be computed with that power series for e to the x. And so this is actually the most sensible way of making sense of the irrational exponents, and not that rational approximation that we talked about last time. So, any questions on the real irrational exponent procedure? And so, the reason that this is a better approach is because this can actually be extended really easily to complex numbers. And to get started, let's go ahead and just take a look at the complex exponential function. Then e to the z, where z is a complex number. Any guesses? Just the same power series we've been doing over and over again. So e to the z for a complex number, same exact thing. Just this power series e. Okay. I know I have some good markers here. I made sure of it. I just have to find it. Okay. And so once you see this, it's almost like we're home free, right? It kind of looks like we're home free, because if we want to define a complex number to a complex exponent, it kind of looks like we can just do the same thing, right? So to define a complex number to a complex exponent, can't we just use that same formula? We express z as e to the log of z and raise that to the w to get the same thing, right? And then you can expand that thing into a Taylor, into its Taylor series expression and compute it. And once again, you would have reduced yourself down to addition, subtraction, multiplication, and division, right? And the answer is yes, it is this easy. The only problem is we have to define what we mean when we say what's the log of a complex number, right? And this is where the fun begins. This is, like I said, this is really good stuff. So, to define logs of complex numbers, we first have to understand the geometry. Let's see, is that where we're going right now? I think we may have. Oh, yeah, no. Let's go ahead and compute e to some complex power real quick, just so that we can get an idea of how this function behaves with complex numbers. Then we'll start looking at the complex log of them. And so the first thing that I want to point out about this function e to the z is is that it's absolutely convergent. Has anyone heard this term before, absolutely convergent? Okay, so an absolutely convergent series is one in which the absolute value, or the size of the terms, when you add up the absolute values of all the terms, you still get a convergent series, okay? It's absolutely convergent. And what that means is this sum here, where you take the size of all these elements, still converges. And the basic idea behind an absolutely convergent series is that the terms approach zero so fast that the size of all the terms never adds up to anything much, right? And so to get an idea of what this absolute convergence, like to gain some intuition for it, I think it'd be good to consider something that's not absolutely convergent. And so let's do this non-example here, where we consider this alternating series here, -1 to the k over k, with k running from 1 to infinity. This thing here is just, alternating fractions, right? The first fraction is going to be -1 over 1. But then for k equal to 2, the sign switches to positive. So we get 1 over 2. And then -1 over 3, plus 1 over 4, and so on. And so this is an alternating series, right? And so you guys remember how can you determine if an alternating series converges? Don't remember? An alternating series converges as long as the size of these things approaches 0. So in this case, we see that this thing's 1, this thing's 0.5, 0.33, 0.25. So the size of all the terms is approaching 0, and therefore that's the alternating series test. By the alternating series test, this series definitely converges. Size of those things approaches 0, then the sum does as well. Then the sum converges. And so that's all well and good, but what would happen if we took the absolute value of these things? So what if we took the absolute value of -1 to the k, -1 to the k, over k. Took a lot to get that thing written. Okay. So, absolute value of -1 to the k is just going to be 1, right? So this negative term essentially just drops out of the picture to give us the sum of just these values, 1 over k. And anyone recognize this series?
I feel like I should.
Yeah, this is the harmonic series, right? Which says just add up all the reciprocals of the natural numbers, 1 over 1, 1 over 2, 1 over 3, 1 over 4. And this thing is divergent. Okay. So what's happened here is these things, they get small, but they don't get small fast enough to make the series absolutely convergent, right? And so an absolutely convergent series is one in which the terms drop off so quickly that even if you took the absolute value of them, right, these things drop off, but they're also alternating in sign. and that sort of helps even things out to where they sort of reach a finite sum in the limit, right? But they don't drop off quick enough to where when you take the absolute value, it still converges. And so that's what an absolutely convergent series is these terms get small, would have to get small so fast that even when you take the absolute value, you still get a convergent series, okay? And so this e to the z has that property where it's absolutely convergent, meaning anytime you take the size of these terms and add those up, you still get a convergent series. And so can anyone see why this thing, why these things approach zero so quickly?
Factorial?
Yep, exactly. That factorial term is so strong that there's no competing with it. It just approaches infinity so quickly that these terms rapidly shrink down to zero. Okay, so that has a very important consequence in the theory of infinite series, because we've got this series in which the terms drop into zero so quickly that you can add them up. You can add up even the sizes, and you still get a finite sum. And as a result, what this tells us is that we can rearrange these terms any way that we want to. Okay. So a consequence of absolute convergence is that we can actually add these terms together in any order that we want to, and it'll still amount to the same thing. And so you can't really appreciate this until you start playing around with what it means when you don't have an absolutely convergent series. And so if you don't have an absolutely convergent series, then believe it or not, by making clever rearrangements of these terms, you can actually get this sum to converge to anything that you want to, right? And so in a non-absolutely convergent series, after rearranging in some special way, you can get it to converge to any number that you want to. And I thought it would be informative to just talk briefly about why that property holds. How is it that this sum here, you just rearrange things to get any value that you want? And the answer to that is that, let's go ahead and think of some of these negative terms. And using the negative terms, if you went past 10 in this positive sum, then you can end up going 1, minus 1 over 3, minus 1 over 5. You can just sort of back your way up by adding up a bunch of these negative terms. 2k plus 1. And you'll inevitably get a little bit below 10, right? So you can then start adding some positive terms back in there. 1 over 2 times k plus 1 plus 1 over 2 times k plus 2. And each time that you add these extra terms, you're getting better and better values. You're getting finer and finer values, because remember that these terms here, the negative terms, for example, they're all approaching 0. Same thing here, these positive terms, they're all approaching 0. So when you're adding these fractions in here, each of these fractions is getting smaller and smaller as you go, so you have more and more ability to get closer and closer to 10 using these smaller and smaller numbers, right? And so all that you have to do is just get a sum that approximates 10, and then back it up a little bit with some negatives. And then back it, moving forward with some positives, back it up with some negatives, and you can start oscillating back and forth until you literally just start to settle out to where the limit is 10. And so it's all because of this. The negative terms, you have as many of them as you need. The positive terms, you have as many of them as you need. And you just start inching closer and closer to 10. So there you go. So it's absolutely convergent series. You don't have any of that funny business. And you can rearrange the terms in any way that you want, and you'll always get the same sum. Okay? So this e to the z has that property that it's, I guess I've erased it now, that it's absolutely convergent. And so as a result, we can compute these powers in a really nice way by rearranging the series. And so let's compute e to the I, for example. Then we know the power series just says compute all these powers of I. And we know the powers of I all have a really well-defined behavior, right? Because when we get I to the 0, we get 1 over 0 factorial. I to the 1 is going to be I over 1 factorial. I squared is going to be minus 1 over 2 factorial. I to the 3 is going to be minus I to the 4 is going to be 1, right? I squared times I squared is minus 1 times minus 1, which is positive 1. I to the 5th is I. And so we see, oh, okay, all the i's are just repeating the same pattern over and over, right? It goes 1i, negative 1, negative I. 1i, negative 1, and then negative I. And so they just start repeating that same pattern over and over. And because this series is absolutely convergent, we can rearrange it any way that we want, okay? So let's rearrange it by scooping up all the real terms and scooping up all the imaginary terms and putting them in their own two series, okay? So this term here, that's a real term. That's a real term. That's a real term. And we just put all the real terms in their own series. The imaginary terms, let's pull the I out of all these imaginary terms. We get 1 over 1 factorial, minus 1 over 3 factorial, plus 1 over 5 factorial, and so on. And does anyone recognize these series here? Over 2k plus 1 factorial. Anyone recognize those two series? These are the series for sine and cosine, right? This is really, 1, we can really think of this as 1 to the 2k power if you want, right? And this is 1, so we can think of this as the 2k plus 1 power if you want. And so we see looking back at those series for sine and cosine, oh sorry, there's an alternating term here as well. The alternating sine term. And so looking back at those series for sine and cosine that we saw, that is cosine of 1 plus I times sine of 1. And so, strange as it may seem, in the complex world, the exponential function actually gives birth to sine and cosine, right? In the complex world, the exponential function is actually periodic. Really, strange idea, maybe. And this formula holds for pretty much any angle that you want. So here we've got the angle 1. This is in terms of radius, so 1 radian. But it holds for any angle that you want. So in general, if we have e to the I theta, this is equal to cosine theta plus I sine theta. And doesn't matter what angle you plug in there, cosine and sine always fall out as a result. So like I said, those three power series are all closely related, and that's how the power series for sine and cosine literally fall out of the power series for e to the x. And so what we've got is, we've got e to an imaginary number. This is purely imaginary. And you can show, and it takes a little bit of work. It's not difficult work, but there's maybe some tricky algebra that you have to do. You can show that if we have e to the z, where z is a complex number x plus iy, using some tricky algebra on that power series for e to the x, you can rewrite this as e to the x times e to the iy, which this e to the iy we've already seen is cosine y plus I sine y. And so this expression here is a way of rewriting e to the z in terms of two special components that we're going to talk about extensively later on. This is a direction in the complex number system. So this is a direction. And this e to the x here, this represents a length. Okay. So e to the z can be thought of as, you have some complex number pointing in some direction that's been rescaled by a factor of e to the x. Okay. And so I kind of think maybe we should leave it there for now, because you said you have class at 11.
Yes, can you
Yeah, so I think maybe this is a good stopping point. And sorry about the technical